You can come in, guys. No worries. Thank you. Come in, we are open. Come in, we are open. Perfect. Perfect. Right. Yes. I fully agree. A most wonderful good after morning, everybody. Is it too late to wish you all a very happy and successful new year? Nah, I do it anyway. And I hope you had a good break with all your assignments and all that stuff. I can tell on the group chat there is still a lot going on, especially with the BI 302 PCR write-up. When do you have to hand it in? Monday. Today. Today at 12. So it's done. Wow, that's amazing. Because last night I got some emails from people saying, oh, how do I draw a graph in Excel?
Really?
Yes. So, I thought, oh well, better late than never. Right. Please don't let me shout. I know you are excited to see me, and so am I, but I'm excited to see me. Somebody said or suggested on the group chat that it would be good if people could ask questions in lectures, and you probably are aware I had to turn off the comment section because there was a lot of crap in it. But there is a different system that you guys can use, and I will introduce some sort of commercial breaks in the lecture where I can have a look at these questions and then answer them. So what you need to do on your phone or on your tablet or computer, go to this textwall.co.uk/post, and you will be greeted with a sort of a box there, a text box, where you can type a message. You have to put UK, which simply stands for University of Kent. UK in front of your message, of every message that you're sending, and then you type your message and then you click the submit button. Do you want to try out whether it works? Anyone? How are you doing today? Let's see. Hello. Okay, so at least one. Fantastic. So obviously it does work, right? So I will every now and then I will have a look at what's going on here. And if you have any questions during the lecture, post them and I'll keep an eye on it and then try to answer questions, okay?
Sorry, what's the login?
It is, let's go back to that, textwall.co.uk/post and UK. You might want to bookmark that or something like that, because I'm going to use that in more lectures. Okay. And if anyone wants to scan a QR code, here is the code for you, if you insist on scanning that. Okay, brilliant. So it looks like most of the systems work, and that is really positive. So what I want to do with you is I want to repeat a little bit about data analysis and also a little bit about statistics. The reason for that is, again, last night I had an email from a second year student. They are currently doing mini projects about enzymes. I think that's stuff that you are currently doing at the moment. You've started that with Dr. Kat, yeah? And there was some data to analyze, and the student emailed me very clearly at the verge of a nervous breakdown saying, I have a negative Vmax. What shall I do? Well, negative Vmax in enzymes is not a good thing. It's actually not possible to have a negative Vmax. But it wasn't the student's fault. It was just the data were pretty meh. And that's why the student got that. It's perfectly okay. You know, sometimes you measure nonsense, but then you have to have the tools to identify that it's nonsense, and that is what data analysis is all about. Finding out that your data are basically shite. So today I want to do a little bit about, again, confidence intervals and t-tests. And with t-tests, I don't mean that you're sitting in a corner and have a cup of tea and, is that Earl Grey or Lapdog Shoesnog or something like that tea. It is a really useful testing tool. So let's start with that. Let's assume, and let's go to the core of inferential statistics. And in inferential statistics, we want to figure out what's happening in the world. Inferential statistics uses samples to make conclusions or to come to statements about a larger population. So my population is here indicated with these big circle. So that's a population. And each population is characterized by parameters, population parameters. And it could be anything that we are interested in. So for example, in a population, we might be interested in the mean of the members of the population. We might be interested in the variation in this population. So that is usually indicated by this sigma. That is the standard deviation, variation in this population. And yet, usually we don't know these things. If I say to you, how tall is the average British male? No idea. I mean, are they as tall as Chris? You are quite tall, aren't you?
6 foot, I think.
6 foot? Are they as tall as Mark? Charlie. Are they as tall as Charlie? How tall are you?
5'7.5".
5'7.5". That's a little bit.
Well, it's because 5'8", I think the.
Yeah, okay. 5'7.5". Yeah. So are they? Where are they? I have no idea. So usually we don't know the parameters of a population. But we might need to know for certain reasons. And so what we can do is we just simply take samples of this population. So I indicate that with this little circle here. And that would be a sample. And samples are characterized by their what is called statistics. And it's very convenient. Population parameter, sample statistics. So they all start with the right letters. And the sample is characterized when we use the same thing as the population, They are characterized by a mean, and we usually abbreviate that with an x bar. So this is x bar, that means the mean of the sample. We have the variance, that is S, or in this case, the standard deviation. And of course, a sample has always a certain size. I just pick, for example, 10 males, measure them, get a mean of the sample, I get a variability of the sample, that's the standard deviation, and I have a defined sample size. Right? And then I can make a sort of an educated guess how large, how tall people, how tall males in the entire population are. Will I ever find exactly the true average? Will I ever find that? Simone goes like that. No? We won't? Yes, we could. We could find exactly the average of every single male in the UK. How?
Measure every single male in the UK?
You are absolutely right, Chris. Absolute, but you know my approach to life. Life is too short for doing some nonsense like that. Yeah. Life should be exactly. And I'm not going around and measure. Actually, I don't know the size of the British population. I think it's about 66 million or something like that, give or take a few 100,000. But even if you want to measure those, so it's not a good thing. But what we can do is, from this sample, we can construct a certain range, and we just simply say our sample mean is probably representative of the population mean, like that. Sample mean is representative of the population mean. So therefore, what we can do is we can say, right, we have here our sample mean, and we can say, right, probably the males, the average height of UK males is between, let's say, 5 foot and 7 foot. Right? So 5 foot and 7 foot. And we can be fairly sure, if we are looking at adults, we can be fairly sure that this is a pretty good estimate. So if 95%, for example, of the males will be in this confidence interval. Yeah, does that make sense? That is the concept of a confidence interval. I am pretty sure that when I do a lot of testing, that my true population mean will be within this range. Okay? So if you get that, you are on a good way understanding the confidence intervals and statistics. Right, now, let's do a little thought experiment. Let's say, oh, good evening.
Hi, Happy New Year.
Happy New Year. Let's say we take a sample of the males of females. Nobody should be, feel left out of people who are neither male or female, or, I need to be very careful with these things. I want to be totally inclusive. Let's say we take a sample. From this sample, we calculate our X bar, we calculate our S, and let's for a moment assume that we know actually the population mean. And what we then can do is, let's calculate what is called a T statistics. T. And let's just, for fun, let's just define what this T should be, what we want to calculate. We calculate X bar, that is our sample mean, minus the population mean, divided by the sample standard deviation divided by the square root of n, sample size. I mean, we could calculate all sorts of things, but I quite like that because it contains everything that we probably would have measured. We have our X bar in it, we have the sample mean, we have the sample size, we have the sample variability in it. So, does our T actually depend on the sample size? What do you reckon? Yes, it does. And of course, what would happen, for example, you have seen this bit here. S divided by square root of n. Have you seen that before? Yeah? Where? In the margin of error. It's not the margin of error. It's close. What is this? It is the standard error of the mean, or just simply, it's the standard error of the mean. Sample error, yeah, I think you could probably call it like that. Mm-hmm. So you've seen that before. It also has a different name, but I come back to that in a minute. Okay, so we've taken a sample, we've calculated our T statistics for it. So that's the T statistics for our sample. Actually, let's do that again. Let's do that for a different sample. Pick another sample with size n, measure the mean. Will it actually come out with the same mean as before? Same sample mean? Probably not. Why not?
Because there's natural deviation.
You're absolutely right. It will probably not come up with the same sample mean. I might just randomly pick tall men or, short asses like me. So the sample mean will be different. What about the variability? Will this be different? Probably, yeah. Depending on how I pick people. Actually, let's do that again. Let's calculate, let's take another sample and let's calculate another t-statistics. We can do that. And what we can do is actually, we can collect loads and loads and loads of different samples, and each sample has its different t-value. And we can plot these t-values. And what we will find is if we look at sample mean and say this should be the same, actually, no, let me write this different. Let me write it like that. X bar minus mu. If I write that as what is the difference between the individual sample means minus the population mean, and I pretend in this case I know it, what I will get is a really interesting distribution. It looks like this. Have you seen that before? This distribution. Sorry? It is kind of normal distribution. When we talked about the normal distribution, I didn't give you all that crap about the S and the square root of n and things like that. In this case, I do. So this distribution actually depends on the sample size. So this distribution it looks like the normal distribution, but it is a normal distribution in disguise. And because we are doing that over the t-value, this thing has the name of imaginatively called t-distribution. And you are absolutely right. It is also called the student t-distribution. There is quite an interesting story about why it is called student, you know?
No.
No? It is not because students get tortured with it. And we have lots of victims. This stuff was actually invented at the beginning of the 1900s. The McGuinness Brewery, which is famous for what product? Guinness. They struggled with quality control. And they wanted to make sure that their product is always of the same quality. So they said we need to compare different batches of Guinness. So they hired a young statistician by the name of Gossett and gave him the task, find a way how we can actually compare different samples. And he came up with this, what is called a t-test. It should be really a Guinness test, but it was called t-test. And he got really excited because it also involved a lot of sampling, just to make sure that he's sort of on the right side. And then he decided to publish his results. But that is not what the Guinness Brewery wanted. They didn't want to pass on their trade secrets, how they measure, how they compare samples to other breweries. So they asked him to change the name under which he publishes it. And he couldn't think of anything better, but, well, actually, I'm a student of statistics, so he published it under the pseudonym of Student. And that is why it's ever been called Student t-test. So that's basically the story behind the Student t-test. And I think when you learn about this background, it makes it quite interesting. Okay, let me just quickly check if there have been any questions. Okay, good. In this case, I don't think we need to. If it is your birthday today, happy birthday. Okay, so that is our student t-test. How is it different from the normal distribution? It is, again, it's a bell shape. That's absolutely clear. But there is not just one t-distribution. There is not just one normal distribution. There are loads and loads of other distributions, of similar t-distributions. And each t-distribution depends on the sample size. So if you have a large sample size, then your t-distribution will be almost indistinguishable from a normal distribution. If you have small sample sizes, your t-distribution looks slightly different. And the difference is in the weight, in the weight of these tails here. So these tails are fatter, usually, than in a normal distribution. Normal distribution would probably look like a little bit like something like that. So if the number of samples that you have is fairly small, then you have this t-distribution here. If the number of samples is quite large, then you end up with something that looks like a normal distribution. And again, what we can do is we can define a sort of a range where when we do these sampling from our group here, from the population, when we do that very, very often, we end up with that. And we can say, actually, we can define a sort of a confidence interval. So for example, here, this area here that I'm shading at the moment, we can say we expect 95% or 99% or 90%, that's entirely up to us, we expect 95% of these t-values that we calculated to be in this shaded area. So that would be 95%. Well, it doesn't have to be 95%. Now, let's just simply look at, not the way I have drawn it here, but we can look at the red bits here. Assuming that the t-distribution is symmetrical, what would be these red bits in percentage? 2.5 each. You're absolutely right. So 2.5%. Or I could also say, well, actually, there is a 2.5% chance that I get a t-value that is in this red bit here. Or a 2.5% chance that the t-value is in this on this side here. This part here. Well, if I do that often enough, 95% of these t-values, and we are talking about t-values here, 95% of these t-values actually will be in the black shaded area. Now, we can also define something here, which is sort of what is the width of this t-distribution. And we've done that for our normal distribution. The width that we have here I'll try to do that as clearly as possible. This width is defined as the standard deviation for the sample mean. This thing also has the name of this curve is also called the sampling distribution. Sampling distribution of the sample mean. That's this distribution. That's the official name for it. And this bit here, this sigma x bar, is actually called the standard deviation for the sampling distribution of the sample mean. And if you say that 5 times in a row, and you can still stand upright, then you didn't have enough to drink last night. Sometimes it is just simply abbreviated as the sampling standard deviation. But the correct term is standard deviation of the sampling distribution of the sample mean. So why on earth do we give a flying but? Why do we want to know that? Because we can show that this thing here is, oh, okay, I thought I've turned off notification. Ah, that's from the group chat. we can show that the sampling distribution is the same as the population standard deviation divided by square root n. So if we can find this sampling distribution, all we need to do is we multiply the sampling distribution, standard deviation, by square root n, and we get our population standard deviation. And that is, just as a reminder, that is exactly what we want. We want mu, and we want this population standard deviation. Let me just quickly check if I have totally lost you already. Yes, a lot of question marks. That's good starting point. Well, let's not worry too much about the question marks for the time being. Let's just simply say we start with our t-value. The t-value is what we said, something like that. And now the question is, can we actually figure out what our population mean is? Because at the end of the day, this is what we want to know. What I just shown you was a sort of a thought experiment. We just, we know the but we don't know the population mean. But can we calculate the population mean? Hey, yes, we can. We just have to rearrange this equation a little bit. We bring that to this side. We have t times s over square root n equals x bar minus mu. Or if I solve that for mu, for the population mean, mu equals x bar minus t times s over square root n. And you told me earlier, you have seen that before, t times s over square root n, and that was called the loud? That was the margin of error, exactly. So what we have here is basically what we said above. We said we have x bar here of our sample, and we define a margin of error. Margin of error. And we say we are pretty confident that our true population mean is located in this thing. People also call this if we take both sides together, they call that the confidence interval. Why? Just simply because we are fairly confident that our population mean is somewhere in this confidence interval. Yeah? Make sense? Good. You don't have any other options in saying yes. So let's go back to our, yes, James?
Isn't that a circular dependency though?
Absolutely.
We used the population mean to work out t, and then you use t to work out the population mean.
So in the first, you're absolutely right. I'll show you, probably not today, but I show you the next time what the point is. Because we can say, right, I don't know actually the population mean,
You guess one.
but I can guess one.
If the maths all checks out, then.
And I can check whether it is within this 95%. Oh, I tell you what, let's do that right now. Let's do that straight away. And if you get confused, blame James. Right? So, what we can do is we can just simply say, we take our t-distribution. And actually, you don't have to do that all yourself. Clever people have developed programs to do these t-distributions. And I can say, for example, if you have a sample size of, let's say, n equals 3, it's a really small sample. Here are our t-values. We want to know our 95% confidence interval here. What is actually the t-value here that keeps the 95% in there? This thing has a name. It's called the t-critical. And people have developed long lists of tables for a certain number of observations and for a certain confidence, so percent confidence. And for example, I just happen to know the t-value, the t-critical value for n equals 3 and a 95 confidence interval. This value is 4.303. And here on that side, it is minus 4.303. So what I can do now is, but these critical values change according to the sample size and how confident I want to be. Usually we are pretty happy with 95%, but there's no law in the world where you say, oh, you know, I'd like to know only 73%. Be sure about that. Or I want to be 99.9% sure about things. So you can set these confidence limits. So what I can do now is I can say, right, I take a sample of 3. So let's say I have x bar equals 100 and let's say 70 centimeter. I'm from the continent, right? I don't do feet. 170 centimeters. My standard deviation should be, let's say, 20 centimeters. N equals 3. And I assume that the population mean is, let's say, 160 centimeters. That's an assumption. I don't know that. Somebody told me 160 centimeters. So, can I calculate a t-value for that? Of course I can. This would be my t-statistic. T-statistic is 170 centimeters minus 160 centimeters divided by let's not do that 20, let's do 17 centimeters, right? I like that better. Divided by 17 centimeters divided by square root 3. Because then I can do it in my head. Rihanna, what did you get?
1.019.
So we can do the calculation, can't we? And you did it, and I think you did it absolutely right. So we have 170 minus 160 is 10, divided by 17 divided by square root 3 is 1.7 roughly. Is that right?
I got 1.017. Oh no, 1.019. Yeah.
So, thank you. So we get roughly for that, if we do that, 1.09, 1.1.
1.019.
So let's do 1.1, roughly. Yeah? So I can calculate from that my statistics. Now here is the big question. What do I do with the statistics now? I can actually go up into my t-curve and ask the question, is this t-statistic of 1.1, where would that be on my curve here? And I forgot to say that the maximum of that curve is at 0. Would a t-value, a t-statistic value of 1.1, would that be included in this 95% region or not? Yes or yes? It would be probably around here. So here would be my t-statistics. Should I be surprised that I find this t-statistics? Should I be surprised that I get this value? No. Should I be surprised that mu is 160 centimeters? No, because it gives me this t-statistics. Okay, in a different test, t-statistics, I get a t-value of 7.9. I just made that up. Comparing it to my curve, where would be 7.9? That would be pretty much here, right? Should I be surprised to get this t-statistic? Yes, absolutely. Because it's way out of my 95% confidence interval. So by calculating a t-statistic and with a sort of an assumed population mean, I can check whether this assumed population mean actually is surprising or not. And usually in science, if it is surprising, then hey, there is something going on. wow, I need to investigate. If it is bog standard, 95% confidence interval, yeah, who cares? Boring stuff. 95, yeah. It's not worth it just confirms my beliefs. But I get a t-statistic of 115, or I get a t-statistic of -15 or something like that. Oh, wow, cool. That is totally not what I expected. This is a little bit like, we had this example with the pizza. I expect a price of, say, between 8 and 20 pounds. Now, here, I get charged 187 pounds for a pizza. First, I would say, eat it yourself, stick it somewhere, but take the jalapenos off first. Or I would investigate, why the heck is it so expensive? Maybe there is gold on it. And then give me that pizza. Okay? So, very quick check. Okay, what is the minimum number of samples? What is the minimum sample number? The minimum sample number is actually 2. But your error gets really, really big. And the t-distribution becomes a normal distribution and much easier to deal with if our sample size, if n is over 30. So ideally you want to have a large sample size because then you can be even more certain that your numbers are correct. Are you happy with that? Go in peace, but don't forget to submit your online quizzes. Thank you very much. Take care.